Right, so here's the second lesson looking into probability calculations with a focus on what we call conditional probability, which is the probability of something in which we don't look at all possible outcomes. We look at a certain subset of that or some sort of condition. We call that a given. We know something's happened, and so how does that change the probability of something else occurring? And let's look at an example here. So first, we have a Venn diagram here showing 60 executives attending a regional conference, and this shows the number of those who've done business in Angola and Mozambique, A and M representing those people who've done business in those countries. So first, how can you tell that A and M are not mutually exclusive? We know they're not mutually exclusive because these two circles overlap. The fact that there is this region that they have in common, there's three people who have done business in both Angola and Mozambique, that's how we know they're not mutually exclusive. If these two events were mutually exclusive, as a Venn diagram, the circles would not overlap. And so that's how I know. I'll say, because the events overlap. Or I could say this, that means that the number of people in where A and M is not 0. So another way of looking at this is if, again, this equaled 0, then we would know they were mutually exclusive. All right, so that's it. I have two questions here of examples of conditional probability. The first one I want to solve just by looking at the Venn diagram. The second one I want to solve using a formula. I can do either for each. So what's the probability that if we chose someone at random, that they've done business in Mozambique, given that they have done business in Angola? So we know they've done business in Angola. What's the probability they've also done business in Mozambique? So in terms of our conditional probability notation, we write it like this. We want to find the probability that someone has done business in Mozambique, but given, so we draw a vertical line, that they've done business in Angola. So this here is how we'd express this statement in probability notation. And so I want to solve this just purely by looking at the Venn diagram. And so first, what I want to first pay attention to is how many people have done business in Mozambique. Well, that's all of this here. So 18 plus 3, that's 21 people. But that in itself isn't so important. What's more important is I'm not looking at all the 21. I'm just looking at the group of people who we know have also done business in Angola. Because again, that's our given. So really, instead of looking at all of those, I just need to pay attention to, I'm just looking at this group here. This 15 plus 3, that's my denominator. That is the number of elements in the set we're looking at. I'm not looking at all 60 people. I'm only looking at those who have done business in Angola. And so in terms of my probability, for my fraction here, my denominator is not 60, it's just 18. Because again, I'm only looking at those people there because we know we have a given. We know that they've done business in Angola. So I know that's my total group. Of that total group, who has done business in Mozambique, just this section that overlaps right here, the 3. So I have a 3 in 18 chance, which reduces to 1/6. So that's the probability that someone has done business in Mozambique, given that they have done business in Angola. All right, so that said, if we have a Venn diagram, quite often that is the best approach. We don't have to look at any formulas or overcomplicate things. But we can also solve it other ways, and plus quite often we don't have a Venn diagram. So over here, this means the probability that they've done business in Angola, but given they have not done business in Mozambique. Now I can solve this as well looking at the Venn diagram, totally can. But for just sake of variety, I want to approach it like this, where if we want to find the probability of any conditional probability, the condition, given in this case B, that's the probability of that is my denominator, whereas my numerator is the probability of both occurring, of the intersection between them. All right, so as an example, here, in terms of just that formula, I would find the probability of both having done business in Angola and not having done business in Mozambique, because that's the complement of M, divided by the probability that they have not done business in Mozambique. Okay, so what's the probability they have not done business in Mozambique? That's my denominator. I'll look at that first. So going back here, if you've not done business in Mozambique, that's all of this and all of this. So that total 15 plus 24, which is 39. So the probability that a person chosen at random has not done business in Mozambique is 39 out of 60. That's my denominator. All right, for my numerator, what's the probability that they've done business in Angola and not in Mozambique? So again, looking up here, looking at what we've done business in Angola, that is all of this. But I know I want to find the intersection between that and those who have not done business in Mozambique. So I'm looking at the intersection between this and everyone who's not in the Mozambique circle, which means I'm looking at just this portion here. Those 15 people, that's the intersection between those who have done business in Angola and have not done business in Mozambique. That's what my numerator is. So it's 15 out of the total 60, because these are probabilities. That said, this simplifies to just 15 over 39, which simplifies to 5/13. Now, this same idea, I could have used the same sort of formula here up here, and I would have got the same answer, and vice versa. I could have just used the Venn diagram for both. Just want to give an example of each. The key to this is always being really clear what is your condition, and therefore also what does the numerator mean? This is the intersection between these two. All right, so in the back, a game is played whereby a dice and a coin are thrown. If the score on the dice is 6 and the coin is heads, the player wins $20. If the score on the dice is not 6, but the coin is showing heads, the player will win $1. Otherwise, the player does not win anything. All right, so first let's describe the probabilities on a tree diagram. Now, if I go by rolling a 6-sided dice first, you may be tempted to draw 6 little branches here. However, all that really matters is, did they roll a 6 or did they not? So I'm just going to make 2 branches. That they rolled a 6 and that they did not roll a 6. That's it. If I leave it like this implies the probability of each is equal. Both, for example, a 50% chance. That's definitely not the case. So there's only a 1 in 6 chance they did not roll. They rolled a 6, and there's a 5 in 6 chance they did not. So I'm going to label those probabilities there. Otherwise, I'm implying it's equal probability of both. After that, we flip a coin, and you have either heads or tails. And for that, it's the exact same probability for each, half for each. I'll still label the 1/2, although it's somewhat implied. All right, so there's my tree diagram. Keep in mind, if I want to look at any one of these pathways, let's say the probability of not rolling a 6 and flipping tails, the probability of that would be 5/6 times 1/2, because these are independent events. What comes up on the dice has no bearing on the outcome of the flipping the coin, and since I have the probabilities of these separately, I can just multiply them together. So with that said, what is the probability the player will win $20? Well, they win $20 if it's a 6 and heads. So that's this pathway here. So it's 1/6 times 1/2, which is 1/12. 1 in 12 chance of winning $20. What about just winning $1? Well, that was if they do not roll a 6, but it's still heads. So that becomes this pathway. I will try to show right here. That's this pathway right here. If you here and heads, that's the pathway to winning $1. It's not a 6, but you still had heads. So that's 5/6 times 1/2. Which is 5/12. Okay, so now we have a given or a conditional probability here. What is the probability that the player will win $20 given they rolled a 6? So if we know they rolled a 6, what's the probability they'll win $20? I'll work it out 2 ways. I'll use that same sort of formula as before. So what's the probability they'll win $20 given they rolled a 6? Well, first, what does it mean to win $20? To win $20, that means that's this pathway I've highlighted in yellow, which I've already found the probability of here, 1/12. 12th. So I'll say the probability, that's the probability of, if I look right here in this pathway, that's the probability of getting a 6 and then a heads. That's winning $20. That exact order, a 6 and then heads. And so I want to find the probability of that happening, 6 and heads, but given they rolled a 6. So that I could show it like this. And so how do I find that? Well, I want to find the probability of where 6 and heads intersects with just a 6 divided by the probability of just rolling a 6. Well, the probability of just rolling a 6, the denominator, is the easiest part, I think, just 1/6, a 1 in 6 chance. The probability of rolling a 6 and a heads intersecting with just rolling a 6. Well, if I look here, this is the probability of 6 and heads. I'll show in purple, this is the probability of just rolling a 6. So this pathway and this pathway here. That's it. I want to find the intersection of these, where these overlap. It's the first thing I drew. It's what you see highlighted in yellow, right? That's where they overlap. So to make this a bit cleaner, the probability, the intersection between the probability of a 6 and a heads and just a 6 is that same pathway, the 6 and a heads. So the intersection of them, which again, we've already seen is 1/12. And so this simplifies to just 6 whole. You actually get, sorry, 1/2, I mean to say. You end up getting 6/12, which is 1/2, 50% probability. That said, to be honest, if I already have the tree diagram, I think a better approach would not be to use that formula, would be to look up here and think about the context of the question using the visual. So what is the probability the person will win $20 given they rolled a 6? Well, if we know they rolled a 6, then we don't even have to worry about this part here. We can just ignore that. So if we know they rolled a 6, we know we're already at this stage right here. And at this point, if you've already rolled a 6, the chance of you winning $20, I can just see, is 50%, because once you roll a 6, you only have 2 choices. You either have heads, in which case you win $20, or tails, in which case you win nothing. So if you know you rolled a 6, all I need to look at is this one part here, and then I can just realize it has to be a 50% chance. And in many ways, I find that far superior than just by default going to that formula. And quite often we can do this. So while that formula is always correct, quite often if we already have a diagram, if we truly understand what conditional probability means, then quite often we don't actually need to use it. I can just see there must be a 50% chance of winning $20 if we knew we rolled a 6. All right, lastly, just for some nameless events, A and B, whatever they are, I don't know. The probability of A is 0.4, the probability of B given A is 0.5, and the probability of A, the union of A and B is 0.75. So I want to find 2 things, the probability of A and B, intersection, and just the probability of B. So a few ways of doing this. I want to do this a bit more numerically, although again, I could try to set up a Venn diagram. So we know the probability of B given A is always going to be the same as the probability of B intersecting with A divided by the probability of just A. That's just using our conditional probability sort of formula. Well, we know a bunch of this. I know the probability of B given A is 0.5. And I know the probability of A is 0.4. As well, the probability of B intersecting with A is the exact same as the probability of A intersecting with B. The order of these doesn't matter, which is one thing I'm trying to figure out. I'm trying to figure that out right here. So really quickly, multiply both sides by 0.4. I can see that the probability of the intersection of A and B happening is 0.5 times 0.4, which is 0.2. There's half my answer. All right, what else can I use? Well, I can use what we've learned actually in the previous lesson, that the probability of the union between A and B must always be the same as the probability of A plus the probability of B minus where they overlap, minus the probability of the intersection of A and B. Well, notice a lot of these I know. The probability, the union of A and B is 0.75. The probability of A, we've seen is 0.4. The probability of B is what we're trying to figure out. And the probability of A and B, we just figured out. So I can just substitute these in. I get 0.75 equals 0.4 plus the probability of B minus 0.2. Isolate the probability of B, and you should get 0.55. Now that's it. Just for a quick check, I want to make a Venn diagram of these probabilities. So I have two events, A and B. I know they overlap. And from what I have figured out here, I can see that the probability of where they overlap, that's this part right here, is 0.2. So I'll put 0.2 right there. I can see that the probability of just B occurring is 0.55. Well, that means 0.2 plus something equals 0.55. So that means the rest of this circle must be 0.35. I can see from the start the probability of A occurring is 0.4. Well, that means that whole circle for A must be 0.4. I already have 0.2 in the intersection part, so there must be another 0.2 right here. And so that means if I look at this, all of this here, if I add it all up, I get 0.75. That's the union of A and B, which is exactly what I see up here. The probability of the union of A and B is 0.75. So I can see this is correct. And to be honest, I could have, using logic, I could have created a Venn diagram first, then solved everything. But in this case, it was probably easier just to use these equations. And that's it from me.